Ladies and gentlemen, welcome to the Hong Kong IE Civil Division event, technical webinar on travel behavior modeling to understand demand for emerging mobility services, organized by the Hong Kong IE Civil Division and the Polytechnic University. I'm the MC of today. We are honored to have Dr. Sunghoon Jang, who received his PhD degree in transportation planning from the Eindhoven University of Technology in the Netherlands. Prior to joining PolyU as an assistant professor, Dr. Zhang worked as a postdoctoral researcher at the Eindhoven University and as a senior researcher at the Seoul National University. He is an expert in advanced travel behavior modeling, aiming to promote citizens' sustainability and active travel behavior to contribute to green transportation. Without further ado, I would like to invite Dr. Zhang to deliver the talk. Dr. Zhang, please.
Okay, so nice to meet you. This is Dr. Sunghoon Jang. As announced, I'm an assistant professor of transportation engineering at the Hong Kong Polytechnic University. So before I start my presentation today, let me first introduce our department briefly. So our department, the Department of Civil and Environmental Engineering, called the CEE at PolyU, we are globally well recognized. So first of all, the 28 faculty members in CEE, so they are the faculty members ranked at the world's top 2% scientists by the Stanford University. And also, our CEE at PolyU is globally well recognized. First of all, we are ranked in top 14 in terms of the best in civil and structural engineering by the QS World University rankings. And also, we are top 3 in civil engineering by Shanghai Rankings global ranking. And also, we are top 2 in the transportation science and technology by the Shanghai Rankings global ranking. Also, we are top 47 in the environmental science and engineering. Also, we have lots of faculty highlights. So first of all, one of our faculty member is the member of Chinese Academy of Sciences, and also 7 scholars. They are so-called the Changjiang scholars by the Chinese Ministry of Education. And also, one of our faculty member is the fellow of the Australian Academy of Engineering and Technology. And also, one faculty member is the fellow of the Royal Academy of Engineering in UK. So based on this world's recognition, our department have shown the amazing achievement in terms of the research funding. So for instance, in the theme-based research theme in Hong Kong, lots of our professors, they received a huge amount of funding from the Hong Kong government. And also there are lots of cases such as Green Tech Fund and also the Lantau Conservation Fund. And also, RGC Collaborate Research Fund, and also RGC Research Impact Fund in Hong Kong. So based on these amazing expertise of our faculty members, now we have multiple academic programs. So now we have a Bachelor of Engineering theme in the Civil Engineering and Sustainable Development. And we have 2 master programs, Master of Science in Civil Engineering and the Master of Science in Environmental Management and Engineering. And also we have a Master of Philosophy program and also PhD program. So with this huge amount of the research programs, our outstanding alumni are very active in the various fields in Hong Kong, including the HKSR government and also Mainhart Hong Kong, Aerob and AC Group, and so on. Also, we have lots of the research facilities, including the 30 laboratories and the 2 workshops, and also 1 research center in Shenzhen. So for more detail, you can find it using this QR code. So thank you very much. And then now go back to today's presentation. So today, my topic is travel behavior modeling to understand the demand for emerging mobility services. So this is the contents of today. So I will first discuss about the fundamental background and some recent challenges. And then I will introduce the description theory and the random utility maximization model and the random regret minimization model. So the first part is about the fundamental background. So let's start from a very fundamental question. So why do we need to understand our travel choice behavior? The answer could be followed by the facts that the transportation is all about the result of our travel choice behavior. Our travel choice behavior affects the traffic flows and transit market shares and demand supply interaction in transportation systems, and also urban planning and also infrastructure design. Then the transportation area itself affects the various fields in urban society, including the accessibility, safety, public health, pollution, welfare, and land use. So to understand and be able to forecast the transportation systems and the effects of the relevant transportation policies, we need to understand and we need to able to forecast our travel choice behavior. So in this background, the travel choice models are a key pillar on which the leading transport infrastructure models and the policies are built, especially the value of travel time savings to assess the billions worth of the infrastructure in the major cities in the world. So for more details, our daily life, is nothing but a totality of conscious choices that you continuously make in your daily life. So choice modeling mostly activated in transportation field, but of course, it is also very active in other research domains. Therefore, I can say this is fully the interdisciplinary issue. For instance, in marketing, there are lots of researchers focusing on the consumer choice, especially from ketchup to iPhones. And also tourism, lots of studies discuss about the destination and the location choices. And also environment, there are some big issues about the trade-off between nature and safety. And also in the area of the energy, there are lots of the discussions on the tax incentives for solar panels, also the adoption of electric vehicles, and also health economics. They focus on the lifestyle or dietary choices, also the patient preference for the treatment. So with this background, let's discuss about the recent challenges in the transportation area. So first of all, the recent development of the information and communication technology, so-called the ICT, it allows the various sharing mobility, the concept of the sharing mobility, and also many emerging so-called on-demand mobility services. So these better improve the transportation sustainability and transportation equity and the transportation system optimization. So the emerging mobility services themselves can be defined as the overall concept of the future transportation services that have become more intelligent and smarter as the existing transportation system and the advanced technologies of the smart devices. So these emerging mobility services themselves are a part of the smart city development. So these days, very recently, all major countries and also all major mega cities, they recently focus on the smart city development. So more than 50%, more than half of the smart city projects are related to the smart mobility. So the emerging mobility services includes the multiple sharing mobility services, such as car sharing, bike sharing, and also the scooter sharing. And also it is related with the multimodal mobility, so-called the mobility as a service. And also the ride-hailing services, including the Uber and DiDi. And also demand responses, transit, electric, and autonomous vehicles, and also park and ride system. So here, the key principles of the emerging mobility services is the clean technology. The clean technology itself means that decreasing the private car use, the gasoline car use. So the transportation moves away from the pollution causing vehicles to a zero emission. And the another principle is the safety. So the purpose is decreasing the fatalities and injuries. And also there are two more aspects of the emerging mobility services are the accessibility and the social benefit. So they should be affordable for everyone and help provide a better quality of life. So in this, within this trend, also the Hong Kong government published the Hong Kong Smart City Blueprint in 2000, if I remember correctly, it was 2017. So the vision in the Hong Kong Smart City Blueprint is that the embracing innovation and technologies to build a world-famed smart Hong Kong characterized by a strong economy and high quality of living. So there are six major areas in the Hong Kong Smart City Blueprint: smart mobility, and smart people, and smart government, and smart living, and smart environment, and the smart economy. So as you can see in this figure, the smart mobility is one of the major areas in the Hong Kong Smart City Blueprint. So here are some social challenges in that. So emerging mobility services, I mean, now these days, now we have a multiple travel options. We can use classical services, or we can use the emerging services. Even we can use the multimodal services by combining them. Therefore, these emerging mobility services have further complicate the Hong Kong citizens' travel patterns because there are lots of the multimodal travel services could be possible. Therefore, it is important to understand how to predict the new demand for the emerging mobility services. So the demand itself, it depends on how travelers prefer to choose emerging mobility services. So a classical way to analyze the traveler's preference is analyzing their choice behavior using so-called the discrete choice model. So the discrete choice model itself is rooted in the discrete choice theory. So this chapter let me first introduce about the discrete choice theory. So for the ease of the understanding, let's focus very simple choice situations. Now we have two alternative transportation mode. The alternative A, the first alternative, is just a classical bus. So this is the classical mobility service. And the alternative B, the second alternative, is so-called the on-demand bus. So let's say the on-demand bus as a O-bus here. So this on-demand bus itself is an emerging mobility service. And then for the simplification, suppose that the only travel time and the travel cost can be observed. And then our aim is to determine the market share of the emerging mobility service, the on-demand bus. So the travel demand should be redistributed across these two mobility services. And then for the simplification, let's ignore any other effects, other external effects, like a competition with a car or induced demand, whatever, just for ease of the understanding. And then the another aim is to decide if the new transit service, the on-demand bus, is worth of the funding. So given reduction of the total travel time in the network, but here one question is that how to value the travel time savings in terms of the money. So let's say about our choice observations in terms of the data. We normally have two types of the travel data. The first one is so-called the revealed choice data. So revealed choice data, it means travel characteristics survey data in Hong Kong. And also other types of any big data could be considered as revealed choice data. But one limitation in the revealed choice data is that the revealed choice data itself is about the existing transportation services. For instance, we can get the revealed choice data for the bus, the classical bus. But in case of the on-demand bus, it's not operated in Hong Kong yet. So actually, we don't have any travel data using the on-demand bus. So in this case, we can use the stated choice data based on the stated choice survey. So the stated choice data is more about the hypothetical travel situations like this, I mean, bus and on-demand bus. So here, I prepared two simple examples. So now we have two options, bus and on-demand bus, and each one had each alternative is described by the travel time and the travel cost. So in the first example, the on-demand bus is 10 minutes faster in terms of the travel time. But it is more expensive, as much as 3 Hong Kong dollar in terms of the travel cost. So here in this observation, the traveler choose the bus. But in the second scenario, the alternatives and attributes are same, but the attribute values are slightly different. So the on-demand bus is 20 minutes faster in terms of travel time, but it is still more expensive, as much as 2 Hong Kong dollar. But in this case, the traveler choose the on-demand bus. So before moving to the mathematical modeling, so how can we use these data, these two observations? So maybe it infers some trade-off between time and cost. So this trade-off related to the value of travel time savings. And also, based on these two observations, we need to predict the choices for other levels of the time and cost. So here, then, so suppose that the Hong Kong citizens' value of the travel time savings is estimated to be 12 Hong Kong dollar per hour. So this means that the Hong Kong citizens, Hong Kong travelers, they are willing to pay 12 Hong Kong dollar more to decrease their travel time as much as 1 hour. So here, then the choice for the bus and on-demand bus for all combinations of the travel time and travel cost can be predicted or simulated. So let's recall the examples again. So here in the first scenario, the first observations. So on-demand bus gives 10-minute gain for the 300 Hong Kong dollar. So it means that on-demand bus is 10 minutes faster, but 3 Hong Kong dollar more expensive. So it means that if these two alternatives are same, then it means that the 1 hour 1 hour travel time has the value as much as 18 Hong Kong dollar. But this 18 Hong Kong dollar per hour is more expensive than the assumed value of time, 12 Hong Kong dollar. Therefore, in this case, the choice should be for the bus. And in the second scenario, on-demand bus is 20 minutes faster, but 2 euros more expensive. So if these two alternatives are equivalent, it means that the 1 hour values 6 Hong Kong dollar. But in this case, the 6 Hong Kong dollar per hour is cheaper than 12 Hong Kong dollar per hour. So in this case, we can simulate it, predict that, okay, in this case, the traveler should be choose the on-demand bus. Okay, then question is that, so what is the limitation of this simple prediction? So the answer is about the human, because traveler, citizens, themselves are human. So, however, in the previous example, the choices assumed to be made deterministically. So deterministically means that in this previous example, we just assume that, so everyone has their value of travel time savings as much as 12 Hong Kong dollar per hour. But of course, in reality, my value of travel time savings will be different with you. Different with others. We may have our own value of travel time savings based on our experience, our daily life, and our any others social norms, whatever. So it ignores heterogeneity across the decision makers. And even within a person, within a traveler, our value of travel time savings can be different depending on the choice situations. For instance, I should, in my commuting trip, I should go to work in the morning. Then my value of the travel time savings will be higher. But in the weekend, now I'm going to shopping. Then my value of travel time savings will be lower. So there are some, the previous way is ignores the inconsistency of the decision makers. So this example is quite simple. So we only talk about two alternatives and only 2 attributes. However, our daily life is composed of the multi-alternatives and the multi-attributes. So we should make a decision based on these conditions. Then the trade-off between attribute and the competition between alternatives would be much more complex. So in this reason, it is necessary for a representation of the choice behavior that allows for decision makers' heterogeneity and inconsistency, and the model representation itself should be econometrically rigorous, and it should be flexible and practical in multi-attribute and multimodal choice situations. So one solution is called the discrete choice model based on the random utility maximization theory. So the model itself is mainly developed by the Professor Daniel McFadden, in the UC Berkeley in economics. And then based on the contribution of the development of this model, the Daniel McFadden, he received the Nobel Prize in economics in 2000 year. So then let's talk more about the random utility maximization model, which the subject itself was received the Nobel Prize in economics in 2000 year. So before talk details about the model, let me first introduce some key elements. So here, the I and J is alternatives. It can be an alternative transportation mode, such as a car and transit, and also it can be a alternative travel route, route 1, route 2, whatever. And then K means about the attributes. So it's about the travel time and travel cost. And X means the attribute values, 10 minutes, 2 Hong Kong dollar, whatever. And here, beta is so-called taste weight. Taste weight for the travel time or taste weight the travel cost. So in the modeling, the beta should be estimated. And the N means individual or traveler. So N is about the human. And the epsilon is about the random error. So based on these key elements, so the random utility maximization model basically assume that people, citizens, travelers, we behave to maximize our own utility. It means that the travelers choose an alternative with the largest utility. So this is called the utility maximizing behavior. But empirical problem here is that any researchers cannot perfectly observe the total utility. We don't know the real value of the utility. This is, I will explain more details later, but because there are some lots of the constraints when we're collecting the data. So the researchers assume that, okay, so the total utility U itself is composed of the observed utility V and the random error, the epsilon. So this is the basic formulation, U equal V plus epsilon. And then the observed utility V is about everything related to the observed attributes, such as travel time or travel cost, whatever observed in the data. And then we assume that the observed utility is based on the linear additive formulation. So V equals sigma beta multiply X. And then the random error, the epsilon, is about the everything else, everything unobserved. So it can include the unobserved attributes. So it's not observed in the data. And also there are some measurement error when collecting the data or randomness in the choices. So because of the random error, the model itself assumes that even when the observed utility V is the highest, the alternative may still not be chosen by a particular individual in a particular choice situations. So in other words, the researchers, transportation researchers, cannot predict their choice itself. So we just predict their choice probability. So it assumes that higher observed utility V and the ceteris paribus, and then it will lead the higher choice probability. So this is called the random utility maximization model. So for the ease of the understanding, so let's recall the previous examples, two alternatives and two attributes. So based on the model estimation with the beta, we can calculate the deterministic utility V. Then because of the effects of the random error epsilon, the total utility can be represented as a certain distribution. Okay. Then, depending on the specification of the distribution of the random error, of course, the different model formulations for the choice probabilities can be obtained. So one crucial computational property is that the choice probability formulation is a closed form. So below is an example. So the closed form itself means that we can calculate their choice probability by hand. I mean, it does not include any integral or other complex mathematical equations. So in the random utility maximization model, when we assume the random error is identical and independent, and it follows the extreme value type 1 distribution, this is called the Gumbel distribution, then we can mathematically get a simple choice probability function. So based on this random utility model, and then based on the strict assumption of the random error, then we can have a choice probability expression. And then the next question is that, okay, so now we have model specification and the choice probability expression. Then next question could be how we can estimate the beta with this model formulation and the choice probability expression. So in the transportation research field, we normally use the maximum likelihood method to estimate the taste weight beta. So the method is to estimate the parameter which maximize the likelihood of the observed choices. So it needs to formulate the log likelihood function and then find the first derivative of the log likelihood function concerning the parameters. And then we can solve the best value of the parameters. So let me explain more detail about this method. So this maximum likelihood estimation method is first proposed by a mathematician, the Ronald Fisher, in 1922. So the method itself is as the sample size increases to infinity, the maximum likelihood estimator of beta is a consistent means unbiased and efficient, and it follows a multivariate normal distribution around the true value of beta in the population. So we can say the estimated betas from the maximum likelihood estimation is an unbiased parameter, unbiased values of the true parameters. So for the maximum likelihood estimation method, we normally use the so-called Newton-Raphson method. So this is the dominant searching algorithm for the iterations in the maximum likelihood estimation method. So the below figure itself can be better to understand this method. So this concave function, this is the log likelihood function for the discrete choice models. Then our objective is to get the peak values. Peak values here, it can be considered as the optimized beta. So the maximum likelihood estimation is, the Newton-Raphson method is that, so from here, from the starting point, starting values, when we normally use the all betas are 0, then based on the mathematical iterations, it searched the top point based on the multiple iterations. So our purpose is to find the values on the top in the concave function. So here we use the first derivation and the second derivation. Okay, so this is the detailed mathematical formulation of the likelihood function of the discrete choice models. And L means the likelihood function, and the P means the choice probability for the alternative J for individual N with the given beta. And theta here is a choice indicator. So if a person N choose the alternative J, then this theta is equal to 1. Otherwise, it is equal to 0. So if it is 0, then this value is just mathematically 1. Then it does not affect the likelihood value here, because multiply 1 is just the same value. And then for the ease of the computation in discrete choice modeling, we normally use the logarithmic of the likelihood function. This is called the log likelihood function here. And then, as I explained before, to find the value of the optimized beta, then we use the first and the second derivation of the log likelihood function here. Okay, then with the estimated betas, we use we can calculate the model fit. So the general example is so-called the McFadden's law squared. So the law squared can be calculated using initial log likelihood value. Initial log likelihood value itself means that the log likelihood value with all betas are equal to 0. And the final likelihood value means that the log likelihood value with the optimized beta. So, but however, here a problem or limitation in this index was that this value itself is increasing as the number of parameters increases. So later, the Professor Daniel McFadden provides the adjusted law squared. So he includes the number of the parameters in the index. And also, of course, we can use the archaic information criterion called the AIC, or the Bayesian information criteria called the BIC. And then based on the estimation result, one of the big advantage of the random utility maximization model is that it can provide the value of travel time savings in a very simple and clear manner. So it benefits provided by the reductions in the amount of the time spent on travel. So this is about that how much are Hong Kong citizens willing to pay more to reduce their travel time. So this is very important in the benefit and cost analysis in many transportation projects, even in Hong Kong or many countries. So in the random utility maximization model, we can just get the value of travel time savings using the very simple ratio between the beta for cost and beta for travel time. Okay, so then an issue here is that compared to the other models, I mean, like a machine learning or whatever, others, statistical or econometric models, this random utility maximization model provides quantitative measures of the preference. So we can use the direct transport, it can directly used in the transport policy measures. So the value of travel time savings are very good, very popular example, but also we can use the log sum, willingness to pay, or elasticity in the transportation planning and the transportation policy. But there are some limitation because now, as I explained, the model itself assumes very strict model structure. So it strictly assumes that V equal to sigma beta multiply X. So this is, but the assumption itself is just assumption. Also choice probability, it assumes the strict logit function. But of course, I mean, this is just a mathematical assumption. So a question is that, oh, okay, so this is the best. Maybe there are any other alternatives. So after the introduction of the random utility maximization model, many transportation researchers have been developed some alternative travel choice models. So the aim is that developing the better model in terms of the model fit. So the development can be summarized in the 3 ways. So this is very simple because the model itself, U equal V plus E. Someone modified the V, the deterministic utility, by applying alternative decision rules. So for instance, instead of the assumption that people behave to maximize their utility, of course, we can assume that people behave to minimize their regret, rooted in the regret theory. So this is called the regret minimizing behavior. And some other researchers, they try to modify the assumptions in the random errors. So instead of the classical assumption, error terms are identical and independent following a Campbell distribution. Of course, we can assume that, okay, the error terms are multiplicative and independent following a Weibull distribution. This is so-called Weibull choice model. And also, some of the researchers, they try to propose some alternative estimation method. So instead of the classical maximum likelihood method, some people propose the hierarchical Bayesian estimation and also the simulated maximum likelihood estimation method. So considering the topic today, today more detail about the random regret minimization model. So here, record the random utility maximization model. We assume that the people behave to maximize their utility. So it assumes that our travel behavior is based on the perfect rationality. Perfect rationality means that, okay, we prefer the short travel time. We prefer the cheap transportation services. Therefore, we are homo economicus. But a question is that, is our rationality still perfect when we evaluate the emerging mobility services? Because the emerging mobility services itself is a new one. I mean, so we are not heard before. So we may feel more uncertainty about these services than our rationality could be limited. So in this manner, if we look at the development in the behavioral economics outside of the transportation area, many scientists, many scholars have found that our rationality is often bounded, limited. So there are some reasons because of the reference dependency or composition of choice set, whatever. So in this situation, prospect theory has been proposed as an evidence of the bounded rationality. And then the theory itself is proposed by the Daniel Kahneman and Amos Tversky. And for the contribution of development of this theory, they also received the Nobel Prize in Economics in 2002 year. So here, one of the most robust and interesting findings from the behavioral economics is that people care less about the absolute levels of the travel times itself, rather than we consider the relative levels. It means that it is more important for us when we choose the transportation mode. In that, for instance, travel time is 10 minutes for the bus. But the more important thing is that, okay, so now I have options for bus and car and metro. So for the bus, how many it is faster than than metro, or how many it is slower than car. This is more important. So the relative to what is so-called the reference point. So the reference point can be many things like the current situation or norms and expectations, or it can be also other alternatives or social peers. So one of the most well-known issue is so-called the loss aversion about the reference dependency, reference point. So it means that we are more sensitive to loss than gain. So here, the loss means that inferior to a reference point. So it means that the travel time for bus is slower than our reference point. And the gain is superior to the reference point. It means that the travel time for the bus is faster than a reference point. So for the ease of the understanding, let me take some simple example. So here, let's assume I expect 20 minutes travel time from Hong Kong to Central. Then, in reality, if I take the bus, it will take 30 minutes. So in this way, the 30 minutes is slower than 20 minutes. So this is the loss. But if I take the on-demand bus, it will take only 10 minutes. So this is 10 minutes is faster than 20 minutes, the reference point. So this 10 minutes is the 10 minutes faster can be the gain. The loss aversion means that, okay, so we have now a loss and gain as much as 10 minutes, but we are more sensitive the 10-minute loss than a 10-minute gain in terms of the travel time. And the another principle is so-called the choice set dependency. So it means that the perceived attractiveness of an alternative depends on the performance of other alternatives in the choice set. So in terms, if the bus is take the 20 minutes travel time, but if the car take only 10 minutes, then we may feel some loss in terms of the bus. But if we say that we don't have a car in our choice set, then there are some other alternatives called the metro. Then it takes 30 minutes. Then we may feel some gain in terms of the bus. So many examples of the choice set dependency of the preference have been studied and are routinely applied in practice and the marketing policies. So-called an example is the decoy alternatives. So I will show you an example more details. And more recently, the theories of the bounded rationality is called regret theory. So the regret theory assumes that the individuals behave to avoid or minimize their regrets. So they assume that the regret itself can be derived from the comparison between alternatives. So if I take the bus, then I compare bus with a metro or car. Then the bus is better than metro in terms of the travel. If the bus is worse than the car in terms of the travel time, then I feel regret. So this is the basic concept of the regret theory. So here, this is about assumptions. So if the bus is better than, if the bus is worse than a car in terms of the travel time, then it is assumed that we feel regret. But if the bus is better than a metro in terms of the travel time, then it is assumed that we feel rejoice in terms of the travel time. And then the regret and rejoice increase with the size of the difference, not the attribute levels, the size of the attribute difference. And then the achieving regret is assigned more weight rate, attaining rejoice, reflecting the loss aversion. And then it is assumed that people choose an alternative with a minimum regret. So this is a little bit, can be distinguished with the previous random utility maximization model. So I have only a few minutes, so I will proceed more quickly. So this is the mathematical formulations of the random regret minimization model. So here, instead of the beta multiply x, they choose the max operator and the beta multiply xj minus xa. It implies the comparison. And then the similar assumptions, error terms are identical and independent following a Campbell distribution. It gives the similar logic function choice probability expression. And then this is the graphical representation of the regret function. So let's assume that the reference point of the travel time is 45 minutes. So if the travel time is faster than 45 minutes in the gain area, it does not much affect on the regret or rejoice. But after the travel time is slower than 45 minutes, the regret is dramatically increasing. So this reflects the loss aversion, reference dependency behavior. So again, compared to the utility-based evaluation process, the regret model assumed the pairwise comparison of the alternatives in the choice set. So the one of the significant model properties are compromise effects. So it means that individuals' tendency to choose the intermediate options. It means that if their performance are overall in simple, we just want to avoid an alternative with a long travel time or very expensive transportation mode. So the compromise effects is one of the most robust empirical findings from the consumer research. So the classical random utility maximization model underestimates the demand for the compromise alternative since it does not reflect any reference dependency or loss aversion, whatever. So for the ease of the understanding, here is a very simple example. Let's assume bus, on-demand bus, Uber in our choice set. And then here is some travel time and travel cost. So here, the bus is the best for the travel time because it's only 10 minutes. But it is worst for the travel cost. It's 50 Hong Kong dollar. But on-demand bus, they are in the middle. So this is called the compromise alternative. But in case of Uber, this is the worst for the travel time, but this is the best for the travel cost because it's the most cheaper. So here, if we apply the classical random utility maximization model, assuming the all betas are equal to minus 0.1, then minus 1 multiply 10 plus minus 0.1 multiply 30 plus minus 0.1 multiply 50, then we can say the observed utility are exactly equal for these three attributes. And then when we calculate the choice probability for each alternatives, then of course, since their observed utility are same, their choice probabilities are exactly same as 1/3. So it's about 33.33%. But here, if we apply the random regret minimization model, so as you can see here, the regret for the bus is 6.29. But regret for the on-demand bus is only 4.51. So the regret for the on-demand bus is lower than bus and Uber. So although their utilities are exactly same, but when we apply the regret model, the choice probability is much higher for the on-demand bus, the compromise alternative. So it gives some benefit demands for the compromise alternative. And then finally, this is a policy implication in terms of the demand of the emerging mobility services. So let's assume this is the current situation here. In the left side, we have a bus, on-demand bus, and Uber. So their performance assumed to be same as shown in the previous example. Then here, the on-demand bus is the compromise alternatives in the middle. So if the compromise effects are valid, then on-demand bus have some more demand than bus or Uber. Then let's assume, okay, now Hong Kong government, they decide to modify the current bus system. So the travel time is dramatically decreasing by applying BRT services. But instead, the cost is increasing. So in this choice set, you can see now the bus is the location of the bus is moving. Then now Uber become a compromise alternative. So if the compromise effects is valid in Hong Kong, then the point is that so in terms of the on-demand bus services, they didn't do anything. They just do as they do, but they lost their demand. Why? Because they lost their compromise alternative position. Otherwise, in terms of Uber, they didn't do anything. They just do as they do, but they can get the additional demand because they got the position in the compromise alternative. So this will be an important issue in the future transportation studies in terms of the demand for the emerging mobility services. Okay, so that's all. Thank you very much for listening. So, is there any question?
Thank you, Dr. Zhang. We will now proceed to the Q&A session. Please feel free to leave a message to the chat room if you have any question regarding the webinar. So if there's no questions, we're going to end today's webinar. Thank you, Dr. Zhang, as the speaker of today. We have prepared carbon credit certificates for you as a token of thanks. I'm sure all of us have learned a lot tonight and hope you have enjoyed the webinar. The digital attendance certificate will be sent to your email in 4 weeks. Once again, thank you very much for joining the webinar, and we wish you a good evening. See you all again in the future events. Goodbye.
Yeah, thank you very much.